Welcome to note set number 24, where we're going to learn about the Z transform, which I call a power tool for system analysis. So we're going to put away the little hand saw and get out the big circular saw to allow us to really analyze discrete time systems and understand a whole lot about them and how they behave. So these are some really important tools that engineers use all the time, at least those who work in this field, to understand how these discrete time systems work and how to design them. So the Z transform is a powerful tool that we can use, and there's two main things that we would use it for. One is to solve difference equations when we have non-zero initial conditions. And we will do that, but we'll do that later in the course. First, we want to continue focusing on this idea of characterizing systems in terms of their frequency response. And this idea of transfer function will be a generalization of frequency response that will allow us to see a lot more about the behavior of the system and will lead to ideas that will help us understand the designs and analysis of very general discrete time, linear time invariant systems. So let's define what the Z transform is, but we're going to creep up on it by revisiting the DTFT. So we've seen this already. We know that it's periodic in omega with a period of 2 pi, and this is how we defined it. We can see that we have an infinite sum here in general, and if you remember from like Calc 2, when you have an infinite sum, you have to worry about whether it is converging or not. So for some signals, this sum here will not actually converge, and then we can apply our tool of DTFT for that signal. And that may be the case also for some systems. We may not be able to find h of omega, the frequency response, because that's based upon DTFT ideas, as we've seen. So what we're going to do is play a little trick to kind of generalize the DTFT to a more powerful setting so that it can handle these problems. So instead of using something like this that doesn't decay at all, we're going to replace it. We're going to stick an alpha out in front, and we can then use alpha kind of as a controlling parameter that we can adjust to make this sum converge. So what we're going to do is now group those two things together to be something that looks like this, raised to the negative n, and we look at this and we go, whoa, that's just a general complex number, so let's give it a name of its own. Let's call that complex variable z. So now we're able to change z, instead of here being limited to things that have unit magnitude, we'll let z be any complex variable value and plug that in up here. So instead of having this thing, we're going to have z to the minus n. And therefore, instead of having this be a function of omega, it's going to be a function of z. And when we do that, we get the Z transform. So for the Z transform, we think of z as in its polar form, so we can think about adjusting its magnitude. We don't really physically do that, but we can kind of think about that. So we want to think about z in its polar form, and replace this by z to the minus n, and there's our definition of the Z transform. And so now this thing will converge for a much wider range of signals. There are some that still this won't work for, but virtually everything that we need to worry about for real-world engineering, this is perfectly suitable for and quite good. And this sum still won't converge for some z values, but you give me a real-world signal, and there's going to be a set of z values for which I can make this sum converge. And so then we just limit ourselves to looking at that particular set of z values, and we don't really have to worry about the others. And we'll give a name to that set of z values in just a little bit. Now, there are two different forms of the Z transform, and which one you use kind of depends on what it is that you're trying to do. And we're going to start out talking about the two-sided Z transform, also known as the bilateral Z transform. And it is just the same one that we had just written down. The minus infinity to infinity, just like the DTFT, except now we have z to the minus n. And this thing is nice because it is very similar to the DTFT, and it allows us to carry over a lot of the ideas and analyze the same kinds of scenarios that we've been analyzing. Now, there is also the one-sided Z transform, also known as the unilateral Z transform, and there, instead of going from minus infinity, we start at n equal to 0. And we will use this later, but the main usefulness of this comes when we're analyzing a discrete time system that has some initial conditions, and we want to find out how the system behaves in response to an input, but also when there were some initial conditions on the system prior to applying that input. So for right now, we'll focus on this and continue our idea of systems that don't have any initial conditions and signals that could start, they could have been running essentially forever or for a very, very long time. Now, we will mention things. We've talked about causal systems, and we're going to just kind of extend that phrase to apply to a signal. A causal signal is one for which its values are all equal to 0 for any n value less than 0. So what we see is that for the class of causal signals, these two forms of the Z transform are identical. There's no difference between them. But when we start talking about non-causal signals, signals whose values are non-zero for values of n less than 0, then we end up having a difference between these. So we're not going to worry about that for right now. We're going to just stick with the bilateral Z transform. So for right now, when I say Z transform, I mean two-sided or bilateral. So we've already seen that when we apply the Z transform to a discrete time signal, we get a function of Z, and Z is a complex value, complex variable. So we're going to have to think about this Z transform as living over a complex plane. So here I'm showing the real part of Z and the imaginary part of Z. So we have two axes that define the Z plane. And we'll often divide the Z plane into two parts. They're the parts that are inside the unit circle and the values of Z outside the unit circle. So the unit circle is just the set of all Z values such that the magnitude is equal to 1. So it's just this circle, right? All the values of Z that are distance 1 from the origin. So we'll be interested in parts that are inside the unit circle as well as parts that are outside the unit circle, and that'll be kind of our dividing line as to kind of the right side of the tracks and the wrong side of the tracks, so to speak. Okay, so now we get to this idea of region of convergence. So just a few minutes ago I was saying that when you try to think about doing this sum that defines the Z transform, it's going to converge for some values of Z, but not necessarily for all values of D. And so each signal that we put into the Z transform will have a perhaps different set of Z values for which that sum will converge. So for a given signal, the whole set of Z values for which that sum converges is called the region of convergence, or ROC. So the region of convergence is just a subset of the Z plane where we can say, hey, that Z transform is well defined. So we're not going to worry too much about region of convergence, but I felt compelled to at least mention it in passing, and it'll come up a few other times, but it's not a big deal in this course. So let's take our unit impulse sequence, or our delta sequence. So it's equal to 1 at n equal to 0, and it's 0 everywhere else, and we're going to find its Z transform, double-sided Z transform, even though this is a causal signal. So we sum from minus infinity to infinity, delta of n times z to the minus n, but really only one term is non-zero. All the rest are 0. So we have 1 times z to the 0, and then all the rest are 0. And z to the 0, anything to the 0, is 1, so it's just equal to 1. And this converges, since there's only one term, converges for any value of z. So the region of convergence is the entire z plane. So what this tells us is that the z transform of the delta function is equal to 1. That's kind of nice. We remember that the dtft of the delta sequence was 1. So this is nice and consistent, since the z transform is kind of a generalization of the dtft. So here's one way of writing that, and there's a table of z transforms, so you should take a look at that. There's a lot of things on there that we won't be covering in detail here, but you need to learn how to use all those. Okay, so let's find another z transform here. So now this is a unit step function, so we put in u of n here, still showing explicitly all the terms, but we know that u of n is equal to 0 for values of n less than n, or less than 0, so we can truncate our sum to start at 0, and from 0 to infinity u of n is equal to 1, so we don't need to actually even put anything in there. And so now we use our geometric sum result again, and we can write this as z over z minus 1, or we can manipulate it, multiply top and bottom by z to the minus 1. So if we do top and bottom by z to the minus 1, z to the minus 1, we can convert it into this form. And we'll see throughout that we are constantly wanting to convert things to in terms of z inverse to in terms of z. And again, we have to think about the region of convergence, and that is set by when does the geometric sum result hold. This actually becomes this only for certain values of z, and it turns out that that is such that all z such that the magnitude is less than 1. So this is all z inside the unit circle. So we say this. Technically, we would state what the region of convergence is, but as I said, we're going to get a little loose with the region of convergences. So we have a nice result here, and that's on the table. We can continue on with this, finding the z transform of a causal exponential. So here's a to the n, and the behavior of this, again, will as we've talked about before, will depend on whether a is a big number or a small number. If a is less than 1 but greater than 0, this thing will decay. If a is greater than 1, it will explode. The unit step just turns it on at time equal to 0. So, but we're not specifying what a is. If you go back and you look at the DTFT for such a signal, we had a constraint that a had to be less than 1. But now we're just going to say, well, a can be any number, and we're not even limiting it to being a real number, although for our uses we don't have any need really to talk about it being anything but a real number. So let's say a is a real number. So we plug that in here, do a little bit of combinations of exponentials, and again apply our geometric sum, and we find that under certain conditions the geometric sum formula will hold and give us z over z to the minus a, and that those certain conditions are all z such that the magnitude of z is greater than the absolute value of a. Actually, I misspoke. The region of convergence is not inside the unit circle, it's outside the unit circle. So I'm sorry for that. So this is saying that this converges for all the z So here's real Z, here's imaginary Z. I draw a circle with radius A, and it converges for all values outside there. Now we can see that if I let A be equal to 1, I get the unit step, and in fact this thing and that thing are then equivalent, and my region of convergence is equivalent. So in reality we could have just found this one and then specialized to the unit step case. Either way. So now the only real thing we're going to fuss about with the region of convergence is this thing when we're going to be able to say the Z transform includes the DTFT as a special result. So if the region of convergence includes the unit circle, then we're able to say, you tell me what the Z transform is, and I'm just going to look at it on the unit circle, and that will somehow give me the DTFT. So basically it's saying we need to go to the unit circle and walk around the unit circle and look up at the Z transform, and the values that we see there as we walk around the unit circle are the DTFT. So when we walk around the unit circle, we're at some angle omega. Z is in polar form. Our discrete time frequency variable is playing the role of an angle on the Z plane. So that's kind of interesting. So here's a surface plot of some Z transform, and you can kind of see this black thing. I was hoping to be able to have it in the notes as being red, but I couldn't quite manage that. So let me fill it in here. Those are the values of this particular Z transform on the unit circle. And so I'll say for this example, the region of convergence does include the unit circle, and so that actually shows us what the DTFT of this particular signal would look like. This also explains why x of omega is periodic, because we're now seeing that the variable omega plays the role of an angle around the unit circle. So once we've walked around the unit circle once, we're right back to where we started. We've gone 2 pi. That's the 2 pi periodicity of the DTFT. So this explains a lot. So basically, we're basically taking that DTFT, that periodic DTFT, and kind of folding it on itself so all the replicas kind of line up when rolled into a circle, and then plunking this thing down onto the Z plane right on top of the unit circle. And then the Z transform just provides some additional values off from the unit circle, some of which will be useful to us, some of which will not. Now the inverse Z transform, there is an integral version of the integral inversion formula, but it's really ugly. It's nasty. It involves complex line integrals. Nobody uses it, so we need some special way to do the inverse Z transform. Now we've been doing inverse Fourier transforms by using a table, inverse DTFTs by using a table. So it's no surprise that we're going to do inverse Z transforms by using a table. And we'll use a tool that will help us do that, and it's called partial fraction expansion, or PFE. I shouldn't have said this. I'm saying it's almost exactly the same as for Laplace transforms. We haven't studied Laplace transforms yet here, but maybe you've studied them in your differential equations class. Yeah, I guess I can say that here. But we will definitely study them later. Now, the only difference from what you may have seen in your differential equations class is when we're doing partial fraction expansions for Z transforms, we need to do a little trick. We're going to first divide by C before doing the partial fraction expansion. And we'll do some examples. There's another video coming up where we'll go into this in a lot of detail, but we'll just do a simple example here. So suppose we've got a Z transform, whatever it is, y of z, and we want to find out what y of n is. And we look on our table and we don't find this thing listed anywhere, and we don't quite know what to do. Well, we can expand this thing out, and then we should find the results on our table. So, like I said, the trick for Z transforms is to first divide by Z. So we're going to divide the left side by Z and divide the right side by Z. So let's back up and see what we had before. We had Z squared, Z, and a constant. If we're going to divide by C, every one of those terms gets bumped up in power. So we'll have Z cubed, Z squared, and Z. And so that's what we actually have here, Z cubed, Z squared, and Z. So the divide by Z is already in there on the right hand side. Now we're going to do this partial fraction expansion using MATLAB's command called residue. So I'll expect that you know how to do this with MATLAB after we've gone through some examples in the next video, but we'll also see how to do some of the simple ones by hand. So you should know how to do them, the simple ones by hand, just in case you need to do one. So to do residue, what we need to do is put the coefficients of the numerator, the coefficients of the denominator into the command. So the numerator goes here, so we have a Z and a constant with a 1 and a 1, so that goes in there. And then here we've got a third power, second power, first power, and there's no zero power. So this 0 here accounts for the fact that there's no zero power. And then the other coefficients go to the left of that. We run that command and it will compute an R vector, a P vector, and a K vector. And in this case, we'll see later what the K vector tells us. But right now, the K vector comes out as an empty vector, so apparently we have no need for that. So since this is third order, we're going to get 3 values in R, 3 values in P. So the R values are called the residues, and the P's are called the poles. So for each one of these terms, so for this one, we're going to put an R up here, and we're going to take Z minus whatever the P was. So we have a negative 0.5, so we're going to have a Z plus 1/2, and we'll have a 4 up in the top for that term. So each one of these terms will have that structure. So I've got it all color coded here. So we've got the 4 and the 1/2, the minus 12 and the 1/4, and then an 8 and a 0. So you know it's like Z plus 0, right? Okay. So now what that tells us is that we've expanded y of z over z to give us that, and then the last thing we want to do is multiply both sides by z. So 4 goes to 4z, minus 12 goes to minus 12z, 8 over z goes to 8. And now I don't actually do the inverse, but what we can do, Jesus, we can go to our table and find each of these terms on our Laplace Z transform table, and we can write down the inverse. I don't think I did it, but oh yes I did. So this term transforms into this term. This one transforms into this, and this 8 transforms into a delta function. So that's how we would do an inverse Z transform using partial fraction expansion. So we'll talk more about partial fraction expansion in the next video lecture, but let's just cover a few more properties here of our bilateral Z transform. There's a bunch of other properties on the table. I'm not going to go over all of them. I'll hit the main one that we need, or the main couple that we need, but you should be familiar with all of these. So linearity, same idea as all that we've had for CTFT, DTFT, the whole thing. Time shift, we've seen this for CTFT, DTFT, And now we'll see it for the zt. So if I know that x of n has a transform x of z, what is x of n minus q? And here we're allowing q to be positive or negative, so we can shift left or right, advance or delay. And the result is we just simply take our original z transform and multiply by z to the minus q. That's a big, big result. A time shift by q is multiplied by z to the minus q. So if we delay by 1, we multiply by z to the minus 1. So this is something that you should be familiar with. Z to the minus 1 corresponds to delay by 1. So big, big, big idea there. That will show up all over the place. Now the proof of this is pretty easy. I put it in quotes because I'm not really doing a formal proof of this. But here's x of z. I've written out, instead of writing it in a summation form, I've written out a bunch of the terms individually. So we have x of 0, z0, x of 1, z minus 1, and so on. I think you see the pattern there. But now I'm going to do this for q equal to 2. So now I'm going to take, when n is equal to 0, I have z to the 0, but I'm actually multiplying z to the 0 by x of 0 minus 2. So that's x of minus 2. And then you can fill in the other components following the same kind of idea. So no big deal there. Now what I'm doing here is I'm factoring out a z to the minus 2 out of every term. So this term here gets broken into z minus 2 times z squared, and so on and so on. So now I've got a z to the minus 2 on every term there. And in the next line, we're going to pull that z to the minus 2 all the way out. I'm getting that thing all set up and ready to go. And what am I left with? 0, 0, 1, 1, minus 1, 1, minus 2, 2. Hey! All that stuff is just x of z. So I have z to the minus 2 times x of z. I shifted by 2. I have at least verified that result for the case of q equal to 2. Very nice. Now, the biggest property is this so-called system property. We've seen it for CTFT. We've seen it for DTFT. So the basic idea is this, that there's some function h of z, which we will call the transfer function, that when I multiply it times x of z, I will get the output z transform of that system. And this holds for LTI, discrete time systems. So this is a huge idea. What we need to focus on is how to find h of z. We've already figured out how to find h of omega, the DTFT version of this, the frequency response. Now we're going to find the transfer function. And we'll talk more about this in subsequent video lectures. But the big idea is input Z transform gets transferred to the output Z transform by multiplication. There's that multiplication again. And so this is a huge idea, and it's similar to what we've seen for the DTFT, similar to what we've seen for the CTFT. So the terminology, h of omega is frequency response, h of z is the transfer function. A lot of engineers get those terms confused. Try not to do that. That's it for this video. Thanks for listening and watching, and I'll see you in the next one.